Good day, everyone. This is the start of the Chapter 11 notes for Physics 1510. This chapter is going to be more about thermal energy itself, specifically calculating the amount of thermal energy that an object has or that is entering or exiting an object, the amount of energy that is needed to melt or freeze something, things to those effect. So, thermal energy is the main key for Chapter 11. Let's go ahead and get started. So, we've talked about thermal energy, and mostly in regards to just setting up how it goes on to affect temperature. Chapter 10 was primarily just about temperature itself. Now we're going to transition back from temperature into thermal energy. And when talking about temperature, lots of different objects can be at the same temperature at the same time. And in fact, if two objects are touching, they will eventually try to end up at the same temperature at the same time. But just because two different objects are at the same temperature does not mean that they have the same thermal energy level. Take, for instance, the image currently on screen. Let's compare 1 cup of coffee that is at 100 degrees Celsius. We're going to take that cup of coffee and we're going to compare it to 1,000 cups of coffee that are all also 100 degrees Celsius. All of these cups of coffee are at the same temperature. If you were to just take random coffee molecules out of each one and check what their average energy levels is, they'd all be the same. But if you compare the amounts of coffee to each other, the 1 cup at 100 versus the 1,000 cups at 100, the 1,000 cups have more thermal energy total as a lump sum because there's more cups of coffee. They're all at the same temperature, but there's just more material present. And all of those different cups have their own amount of thermal energy. There would be 1,000 times more thermal energy in that total amount of coffee because there's 1,000 times more material that needs a certain amount of thermal energy to be at that temperature in the first place. So, how much thermal energy something has does not only depend on its temperature. It also depends on how much material there is. Again, comparing 1 cup of coffee to 1,000 cups of coffee. But it can be even more specific than that. The thermal energy level of an object can be affected by its temperature, can be affected by how much material there is, and it can also depend on what the object is, what it's made out of. Take, for instance, I want you to envision a hot summer day and say that you get into your car. You get into your car, you're going to go to the lake. You're getting in your car to drive to the lake. Now, your car, it's been sitting in the hot sun. And when you go to enter your car, all of the various parts of your car, they've all been touching the same temperature air. They've all been getting the same amount of light from the sun. They're touching the same temperature air, so on paper, they should end up at about the same temperature. But when you get in the car, immediately, the part of the car that you don't want to end up touching is the metal for your seatbelt buckle. If you get in the car and you reach over and you touch the metal part, it's not going to be fun because it gets very, very hot very, very fast, as opposed to, say, the fabric or the leather of the seat that you're sitting on. That feels more comfortable. It's still warm, but it's not hot. It's not unbearable, unlike when you touch the metal seatbelt part. This can continue when you eventually, you get in your car, you drive to the lake, and when you arrive at the lake, you're going to get out of your car, and you'll notice some more similar scenarios. Everything at the lake, the ground, the grass, the water, is all touching the same temperature air. They're all in thermal contact with one another. But when you get out of the car, if your bare feet touch concrete or asphalt that's been in the hot summer sun, it's not going to be fun. It's going to be really hot. It's going to be a lot like the seatbelt buckle. So you're probably going to jump and say ouch and probably try to make your way over to the grass or the water as quickly as possible. And as soon as you're standing on the grass or as soon as you get in the water, it's immediate relief. You are no longer feeling like you're burning because you're not touching the hot thing anymore. But that water and that grass are touching the same temperature air as the concrete is. All of those objects are in thermal contact, so eventually they would reach thermal equilibrium if they're allowed to touch and equalize over time. But what's happening here is those different materials change temperature at a different rate based on what they're made of. Each of those different materials responds differently to the same amount of thermal energy that they're getting in from the sun. So what it's made of also affects how it responds to thermal energy. And all of these things that can affect, all of these things are summarized in the concept of specific heat in the formulas that you're currently seeing on screen. This formula right here, the one that I'm circling, Q equals mc delta T. Q equals mc delta T. This is the specific heat formula, and the purpose of this formula is to show the relationships between the thermal energy that an object has and how it will affect that object's temperature based on its mass and based on what it is made of. So, let's just look at all the different variables in this formula real quick. The big Q on the front. Q is going to be the variable for thermal energy for the rest of this class. You've probably used Q to describe energy. You might have used Q to describe energy in a previous physics class at some point, or maybe a previous chemistry class. Q is thermal energy. And in this formula, that's going to represent the amount of thermal energy that an object is gaining, or alternatively, the amount of thermal energy that an object is losing. So Q will represent change in thermal energy in this formula. Thermal energy is a form of energy, therefore it's measured in joules, like all the energy types we've dealt with so far. And I think that's all the points, actually. So, the amount of thermal energy that an object gains is going to affect its temperature. The things that affect that process are, one, the mass of that particular object. If say I'm trying to warm up, say I'm trying to melt, one handful of ice versus a whole glacier of ice. Those are made of the same thing, but they have very different masses. And because the glacier has a much bigger mass than just a handful of ice, it's going to take more thermal energy to warm up all of that ice. So, mass is a factor. In this formula, it will be measured in kilograms, as the rest of our formulas are. I'm going to skip C for just a minute. We're going to come back to C. The term that's furthest to the right, delta T. This is the object's change in temperature as a result of how much thermal energy it has either gained or lost. If you add thermal energy to something, if you plug in a positive Q, then an object would heat up and its temperature would increase, so your delta T would be positive. If you are, say, taking thermal energy away from something, then your Q would be negative because an object is losing thermal energy, and subsequently your delta T would also be negative because when you take thermal energy away from something, its temperature is going to try to drop. So that's the connection there. The last part of this formula is this little C term here, and this is a new variable. There's going to be a lot of new variables each chapter. This is a new variable that is the specific heat capacity of a specific material. So all of the different things that I've described in this lesson so far as affecting thermal energy, affecting an object's temperature. Amount of thermal energy that an object either gains or loses will affect its change in temperature based on its mass, but also based on what it is made of. The C term, the specific heat term, is the part that takes into account what the object is made of. This constant right here, it's a constant, and every different material on Earth has a different specific heat constant, and that constant just represents how much an object's temperature, let me rewind. That constant represents how much thermal energy is required to change an object's temperature. There's a table here on this particular slide, and this table is of the specific heats of various materials. Let's look at specifically the joules per kilogram degree Celsius column, because that's the standard metric units that we're going to use in this class for energy, mass, and temperature. And in this column, we can see various values for the specific heat of various substances, elements, compounds, etc. And every single one of these has a different number, because every single one of these materials responds to thermal energy in a different way. Different materials heat up more quickly than others. Now, specific heat is specifically a measurement of how much thermal energy is required to change an object's temperature. So looking at this particular list, I want to focus on the smaller numbers first. Let's look at cadmium, copper, germanium, gold, iron, lead, mercury, silver, and tin. All the materials that I just listed are various metals. And metals heat up fast. If you'll remember the example from earlier, the metal seatbelt buckle in your car heats up really fast in the summer sun. It doesn't need much thermal energy to change its temperature. Its temperature will change very quickly because it doesn't take many joules to increase its temperature. So the small specific heat values for the metals are the mathematical representation of that. On the other hand, if a material has a large specific heat number, like the larger numbers in this table, that represents that it takes more thermal energy to change that object's temperature. The single biggest number on this chart is the specific heat of water, 4,186 joules to change the temperature of 1 kilogram of water by 1 degree Celsius. That is a huge specific heat when you compare it to other materials on planet Earth. The next things on this list that even come close are ethyl alcohol, which is a liquid, and the two after that are ice and steam, which are themselves just other forms of water. Water's high specific heat is kind of an anomaly, frankly, but it's an anomaly that makes life on Earth possible. Water heats up very slowly. It needs a lot of thermal energy to heat up. And this is a good thing for planet Earth since water covers most of the planet and it's constantly being bombarded by sunlight that will make it warmer. If water had a low specific heat, if it heated up as quickly as metals, then the oceans would boil from the amount of solar energy that they get that heats them up every day. And that would be a bad thing because the atmosphere would be hot, it'd be full of steam, and life on Earth wouldn't really be possible because the oceans would evaporate. Life on Earth exists because of the specific thermal properties of water, because water has such a high specific heat. This is one reason why it takes a minute to, say, boil water for spaghetti. Literally, it has a high specific heat. It takes a while to heat up. But it makes water a good heat sink, if you've heard that term before. There's lots of machines that use water specifically to keep themselves cool. Think of your car engine. If your car engine isn't properly cooled, it'll overheat and eventually melt if not taken care of. But a lot of machines like that have coolant systems that take thermal energy out of the hot engine and put it into, say, water that is running through pipes within the engine. And since the water's holding on to the energy, the water doesn't heat up as much and the whole thing stays cooler than if the water wasn't there. So water is very important for life on Earth. It has a very high specific heat, and specific heat represents the amount of thermal energy needed to change something's temperature. This rearranged form of the formula here is designed to represent that. The specific heat constant is equal to the amount of heat needed to change the temperature of a certain mass of that material. Now, every single different substance will have a slightly different specific heat. And because there's technically infinitely many of them, you will never have to memorize a single one of them for this class. This table, or a table a lot like it, will be available to you on any questions where you need one of these numbers. So you don't have to memorize any of them. They're available to you as a part of the class. I haven't memorized them because I don't need to, because I have these reference materials, and so do you. If you were to memorize one, keeping the value for water in your head would be pretty good, but you don't have to. You'll be able to reference this at any time. Let's use this formula real quick to start getting some practice in. Been talking a lot about the thermal properties of water, so let's heat up some water. You have a camping stove that can boil 1 kilogram of water, which starts at 25 degrees Celsius. When you put the water on the stove, it begins at 25 Celsius. You turn the camper stove on. You want to make it boil. So, how much thermal energy is required from the stove to make that happen? So, we need an amount of thermal energy, we need Q, that will heat up 1 kilogram of water from 25 Celsius to its boiling point, which in the Celsius scale is 100 degrees Celsius. So we want Q, we know M, we know our delta T, and since we know we're boiling water, we can tab back and check on our table. Specific heat of water is 4,186. And using our new formula, we have everything we need to find that amount of thermal energy. Here's my work shown here. We're going to start with Q equals MC delta T. We are solving for Q because we want to know how much energy this takes. Our mass is 1 kilogram. Our specific heat from the table is 4,186. And our delta T, our change in temperature, we're starting at 25. We need to end at 100 Celsius. This is one of those times where Celsius is legal because the formula specifically has delta T in it. Again, if it's delta T, you're allowed to use Celsius. It's only just T where it has to be Kelvin. Kelvin still works though, but this is one of the times that Celsius is okay. So that's everything except Q. We're able to solve for Q. If you perform your algebra correctly, you should end up with 313,950 joules. That is a lot of thermal energy. I don't want to understand. This isn't a case where the number's big because of the unit. This is just a lot of energy, period. It's a big number on purpose. And that's how much energy it takes to get room temperature water boiling. At least get it up to boiling. You'd have to keep heating it to keep it at boiling to then cook your pasta in. So that's just the amount of energy needed to get it up there. You still need more energy after that to keep it there and to keep cooking. There's a few more samples for this that I want to look at. And this is a fairly straightforward example where we're only looking at one object. But the thing about thermal energy is, by virtue of the fact that energy can't be created or destroyed, if we look at the energy conservation laws, if something gets hotter, if something gets thermal energy from some source, some other object had to lose that same amount of thermal energy first. For example, in the case of the burner here, the water is gaining thermal energy, and it gets the thermal energy from the camper stove losing thermal energy. Anytime one thing heats up, a second thing has to cool down. And their temperature changes will not always be the same. Think, for example, to medieval blacksmiths. They would heat up metal, shape it into a sword, and it's red hot, it's glowing, you don't want to touch it, and then they dump it in water. Suddenly, the entire sword is cooled down to room temperature, but the water itself isn't really that much warmer. The water's still bearable to touch. So, And then this ties back into specific heat. Water's good at absorbing thermal energy, but metal has a very low specific heat, and so it's going to lose energy pretty fast as it cools down. So, thermal energy is conserved. If one thing warms up and gains thermal energy, something else had to lose the same amount of thermal energy. The temperature changes won't be the same depending on what the objects are made of, but the change in thermal energy levels will match. Thus, we have the formula that's presently on screen. Q gained equals negative Q lost. The purpose of this particular formula is to say that whenever one object gains some amount of thermal energy, a different object is going to lose the same amount of thermal energy. If I touch something that's warm and I gain 10 joules of thermal energy from it, that object had to lose 10 joules of thermal energy for that to happen. And this little negative sign here, this isn't a typo, this is important. This negative sign is to make sure that the two sides actually do even out. Because Q gained, one object's going to heat up. It's going to have a positive Q. It has a positive temperature change. On the Q lost side, something is losing thermal energy. It's going to have a negative temperature change. Normally, if this extra negative sign was not here, you'd be setting a positive equal to a negative, and that's technically not equal. That doesn't work. This extra negative here is to cancel out the negative that is inherent to Q lost. Normally, you'll be plugging in a negative Q lost, and you will cancel that out with the negative that's right there. So it's there for a reason, and that's the reason. It's not a typo. Now, this particular formula here is going to utilize the previous one. We're going to start combining them because as one object gains thermal energy and its temperature changes based on the energy and based on its mass, based on its material, something else losing energy will also change its temperature based on those same things. So frequently, the two formulas, Q gained equals negative Q lost and Q equals MC delta T, are going to be used in tandem and combined when you're looking at systems where there's more than one object touching and they are exchanging thermal energy back and forth. Let's look at a new sample problem, the one on this particular slide. You drop a 50-gram piece of copper, and it is currently at 120 degrees Celsius, into 1 kilogram of water at 21 degrees Celsius. What is the final temperature that these two objects are going to reach now that they're touching and once their temperatures equalize? As soon as the copper enters the water and the copper are touching, that's thermal contact, there will be an exchange of thermal energy. Eventually, as long as they're allowed to keep existing and keep remaining in thermal contact, they'll eventually end up at the same temperature. The copper is going to keep releasing thermal energy, the water is going to keep absorbing thermal energy until both of them are at the same temperature and everything is equalized. So the two different objects, the two different sides of the formula we're going to set up will have different starting temperatures, they'll have different masses, they'll have different specific heats, but they'll have the same ending temperature. And I'm going to show that in my work. So, we're going to start with Q gained equals Q lost. Q gained equals Q lost. The water is going to be the side gaining thermal energy, and the copper is going to be the side losing thermal energy. So, on the gained side, we're going to take our Q gained and we're going to replace it with MC delta T, because we know that Q equals MC delta T, and that means that anytime we see a Q, we're free to replace it with MC delta T, and that's exactly what I did here. So on the Q gained side, I replaced it with MC delta T, specifically describing the water's variables in this particular situation. The M on this side is the mass of the water, the C on this side is the specific heat of the water, and the delta T is going to be the water's change in temperature, namely the water's final temperature minus the water's initial temperature. We're going to do the same thing on the right side. This is the Q lost side, and the copper is what's losing thermal energy in this scenario. Pardon. So the water is going to lose thermal energy in this situation. Sorry, I literally just said that the other way. Copper is going to lose thermal energy in this situation. So we're going to replace that Q lost with an MC delta T with the copper's information. So Q equals MC delta T. That's going to leave us with the mass of the copper times the specific heat of the copper times the change in temperature of the copper. On the left side, I'm using a W as the subscript for water. On the right side, I'm using Cu as the subscript for copper. That's the elemental symbol for copper is Cu. So we've laid out our expanded formula. Let's start plugging in our numbers. On the water side, we know the mass of the water is 1 kilogram. We know that it is water, so we're able to look at our slightly modified constant table here, that the specific heat of water is, again, 4,186, so that'll be plugged in for C water. And then for the water's temperature change, that's going to be its final temperature minus its initial temperature. It starts at 21, it's going to end at something else. On the copper side, we're keeping the negative out front. The negative has to stay there. Replacing Q lost with MC delta T, it does not get rid of the negative. The negative is going to work its way out in a minute. The mass of the copper is reported to be 50 grams. We do want that to be in kilograms before we continue, because all of our metric formulas are going to be designed to use kilograms in this class. The C is the specific heat of copper. So we'll look at our slightly modified table here. Specific heat of copper is 387. That'll be what we plug in there. And then the delta T for copper is its final temperature minus its initial temperature of 120 degrees Celsius. Again, both materials will have the same final temperature. So it's the same TF on both sides. Keep that in mind. So that means even though TF is written in two different places, it's still the same variable across both sides, meaning that there's still only one variable in this equation, and we can successfully solve for it. I show my algebra on the next line down here. I have simplified the left side, since we've got 1 times 486, 1 times 4,186 times, open parentheses, TF minus 21, close parentheses. 1 times 4,186 is just 4,186. So I then distributed that value into our parentheses to get 4,186 times TF minus that number times 21. So that's where this number came from. I'm going to do the same thing on the right side. So TF times 0.05 times 387 times the negative sign, because that's out front, that's going to get factored in too, will give us negative 19.35 TF. Then negative 120 times 365 times 0.05 times another negative will create positive 2,322. Again, the signs are important here. The signs on the right side became inverted because now we need to get both the TFs on one side and we need to get both the terms that don't have a TF on the same side. On the left, our TF term is positive and our non-TF term is negative. On the right, our TF term is negative and our not TF term is positive. So this is a perfect opportunity to add positive 19.35 TF to both sides, to get both TFs as a positive on the left, and to add positive 87,906 to both sides to put it as a positive number on the right. So now our left side has all TFs that are all positive, and our right side has all non-TFs that are all positive. Since both the terms on the left have a TF in them, they can add up normally, which is good. So there's just a little bit more algebra to arrive at a final temperature of 21.46 degrees Celsius. This is the correct final temperature. Notice that is only about half a degree hotter than the water was to start with. The water increased in temperature by half a degree. The copper decreased in temperature by nearly 100 degrees. And that's entirely because of the differences in their specific heat, but also the differences in their mass. There was just a lot more water present. A big mass of water acts as a really good heat sink, so it's able to absorb all that thermal energy from the copper while barely changing its temperature itself. That's why water is a good heat sink, and that's why it's good that the oceans are made out of water instead of any other material. We will resume with some more examples of this in the next part of the chapter 11 notes. So stay tuned for that, and let me know whenever you have any questions at all. Thank you very much. Have a nice day.